Hey everybody, welcome back to chemistry. And so I want to continue talking about the Born-Haber cycle as applied to the formation of a ionic solid, which in this case we're looking at is sodium chloride. So now what I want to do is do some problem solving. And so we have a great example of that here. So if I can blow up the slide. It says, determine the value of the lattice energy of the ionic compound sodium chloride using the enthalpy changes of the reactions below. Okay, so the way you solve this problem is through something you learned about in the previous class, which is probably Chem 109. I have some instructions there that could be useful. And so maybe the first step to solving this problem is identify and write out the target equation. And this particular problem is going to be the lattice energy for sodium chloride. Then carefully note what is on the reactant side of the target equation and the product side of the target equation. Okay, then the next step is modify the equations given to you if necessary by either flipping the equation and changing the sign of the change in enthalpy, or multiply the equation and the change of enthalpy by coefficients. And then the next step is cancel out terms, which are usually chemical symbols, so that the only ones left are a part of the target equation. And then finally, the last step is add up the changes of enthalpies of the modified or unmodified given equations to find the change of enthalpy of the target reaction. Okay, so if I can reduce the slide. Okay, so what I'm going to do is I'm going to try to figure out what the change of enthalpy is for the formation of solid sodium chloride from its ions. And so that change of enthalpy is also called a lattice energy. So the first thing I want to do is I want to write out an equation for the lattice energy of sodium chloride, and that will be the target equation. Okay, so here we go. So I'm going to write the equation down here. Gives me some room up there. So the goal is here is we have to write an equation describing how sodium and chloride ions get together and form a solid sodium chloride salt. So let me just write out the product first. And the product is sodium chloride, and it's a solid salt, so I'm going to put an S here, so it's in the solid state. Okay, now for equations describing lattice energy, you may recall that what we're doing is we're bringing together ions in the gaseous state. And so the ions we're going to bring together here are the sodium ions and the chloride ions. So let me write that out. So we're going to have sodium ions here in the gaseous state, and we're adding to them the chloride ions in the gaseous state. And then they will approach each other and bond to one another and form solid sodium chloride. And so what we're trying to find is the enthalpy change of this reaction. So the delta H of this reaction, which is also called a lattice energy. So maybe I should just indicate that this happens to be the lattice energy for the formation of solid sodium chloride from its constituent ions in the gas phase. Okay, so I think it may be helpful for the moment just to color code things. And so what I'm going to do is I'm going to have sodium in red and chlorine in green. So here we have a sodium ion here, and we'll have that in red. So no, this is an ion here. So again, this is the gas phase. And then chlorine here in green, Cl minus, gas phase. And then what we're going to have is solid sodium chloride. And so here it's sodium, which is still an ion in the compound, even though you don't see the sign there. And chloride is still an ion in the compound there. And then this is going to be in the solid phase. And again, these things here, do this in blue, like that. This is our target equation. All right. Yay. Okay. So what I'm going to do now is I'm going to write out the given equations on the screen. So I'll need a moment to do that. So I'm going to color code them as well. So here we go. Okay, so what I've done is I've rewritten the equations that you see on the PlayPosit slide. And what I've done is I color coded the reactions. So the reactions that involve sodium I have in red, and the reactions that involve chlorine I have in green. And you'll notice here, this lower reaction is kind of a mixture of sodium and chlorine, and I'll talk more about that in a second. What I want to do is I sort of identify what these reactions are. And so this first reaction here is you're taking solid sodium metal and you are subliming it to a gas. And so this is just a sublimation. And so the enthalpy change for the sublimation is plus 108 kilojoules per mole. And I'll just leave out the kilojoules per mole. Okay, the next thing I'm hoping you can recognize is that we're taking sodium atoms in the gas phase, and then we're going to hit them with energy, and that's going to ionize them. And you're going to release sodium positive ions and electrons. So this is the ionization energy of sodium. And also, the change of enthalpy here is written as 496 kilojoules per mole, and it's an endothermic reaction. Okay, the next one involves chlorine. So if you look carefully, this may be a little difficult to see, but if you look carefully, you see Cl2 there. Think of that as two chlorine atoms that are bound together. They're held by a bond. And then what you're doing here is you're adding energy to break the two chlorine atoms in the bond and release the chlorine atoms. So that here, 2Cl, is the released chlorine atoms. And so here, you're going to need 244 kilojoules per mole of this to break the bond to release the chlorine atoms. So this is really a bond energy for chlorine, so I'll just write Be there. Okay. And then the next step is where you take neutral chlorine atoms and then you add the electrons that maybe you got from sodium. And then when you add electrons to neutral chlorine atoms, you get chloride ions. And so this is going to be an exothermic process. And you might recognize this as an electron affinity reaction. So the last equation is kind of interesting. This is something you haven't seen in a while. We talked about this kind of equation 109. And what this equation is a description of the formation of solid sodium chloride from its constituent elements at room temperature and pressure. So as you can see, sodium chloride is made of sodium and chlorine. So sodium and chlorine must be the reactants. And so sodium at room temperature and pressure is in the solid state, so we have NaS here. Chlorine at room temperature and pressure is in the gaseous state. So that is a correct state for chlorine here. And so we also had to balance the equation. So you might remember when we're writing out these equations for the formation of a solid ionic salt, we have to have the formation of 1 mole of the ionic salt. And so we have to balance the reactants accordingly. And so here we'll have 1 mole of sodium, but really we need here a half mole of diatomic chlorine to make sure the chlorine atoms balance. Okay, so again, this is heat of formation or enthalpy of formation. So I'll write, this can be written in a lot of different ways. I'll write heat of formation. And just to remind you what this looks like, it's delta H F. Okay, so now what we're going to do is we're going to modify these reactions in such a way that we can get almost all the symbols to cancel out. And after they all cancel out, we're going to leave here with just here the target equation, which was what we want, which is the equation that describes the formation of solid sodium chloride from its ions. Okay, so where do we start? Okay, so that is a really good question. So one thing I notice immediately is in the target equation, you can see you have solid sodium chloride on the right side of the equation. Here, in the heat of formation equation, we also have it on the right side. So I think we want to use this equation as is. So what I'm going to do is I'm going to go ahead and rewrite the equation down here. Okay, so what I've done is I've rewritten the heat of formation equation down here. And because I'm going to use this equation as is, I didn't flip the equation, nor did I add any coefficients. We're going to use the energy as is, which is negative 411 kilojoules per mole. Okay, so what do we do next? Well, I want you to notice something important. So you see here on the reactant side, in the target equation, we have sodium plus ion, right? But here in the heat of formation, it's not sodium plus ion. So what we're going to have to do is we're going to have to take this solid sodium, and then we're going to have to take one of these equations and use it so that we can cancel out solid sodium, because we don't want this here because it's not in the target equation. And eventually, instead, what we want is going to be on the reactant side, the solid positive ion. So let me tell you what I'm kind of seeing right now. So one of the things I can see is that I can take this first equation and flip it, and that will get rid of the solid sodium. And so let me go ahead and do that right now. I'll write this here. And so I've just completely written this here. And so what I did is I took the first equation, I flipped it, and I also had to change the sign of the energy. Okay, so now we're getting a little closer. We have sodium gas, but in the target equation we have sodium positive gas, or the ions. And so let's take this second equation and flip it, and I think that will solve the problem. So I'll write out the second equation flipped. So I wrote out the second equation flipped, and then I changed the sign of the energy. Okay, so let's just see if some things cancel out the way we hope. So one thing you can see is we have solid sodium here on the left and solid sodium on the right. So these cancel out really nicely. So that's great because we don't have solid sodium in the target equation, okay? Also, we have sodium gas on the left side that cancels out with sodium gas on the right side. That's great that we cancel those out because that's not in the target equation. However, we have left here as a reactant sodium ions in the gas phase, which is great because we want that in the target equation. Okay, now we have to do a couple of things. You see this electron here? This electron is not part of the target equation, so we have to get rid of it. And at the same time, somehow we're going to have to do some manipulations such that we can take 1/2 chlorine in the gas phase and get that into chloride ions. Okay, so how can we do all those things? Ugh. So this is a little tricky to see, but one thing I need to do is I got to get rid of these diatomic chlorine atoms. They're going to have to cancel out. And so the only way I can really get rid of them is, you see this third equation here? I can flip it. So the diatomic chlorine atoms will be on the product side, and it will cancel out with the diatomic chlorine atoms on the reactant side. But it gets a little worse. You can see that we only have 1/2 mole of this. And so what we're going to have to do is take this equation after flip it. We're going to have to multiply the whole thing by 1/2. So let me go ahead and set that up. Okay, so what I did is I took this third equation and I flipped it. Now this is a little bit difficult to see, but just please follow me. Okay, so here we inevitably in the target equation want chloride ions, and so we want to get rid of this diatomic chlorine molecule here. Here we have a 1/2 mole diatomic chlorine, it's on the reactant side. Here we have a full mole on the product side, but we're taking this equation by 1/2, so it's really a 1/2 mole here. So at this point, we can cancel out the 1/2 mole chlorine that's on both sides. Okay. Now, the last thing we need to do is somehow we got to get rid of, what, 2 times 1/2? We have to get rid of the mole of chlorine atoms and get these into chloride ions. And so to do that, all we have to do is take this fourth equation and flip it. So let me go ahead and write that in. So what I've done is I've taken the fourth equation and flipped it, and also I changed the sign of the enthalpy. So just to clean things up a little bit, I'm going to erase the top part of the screen. Okay, so let's see if we can finally cancel out some things that we don't want. So we have chloride ion on the reactant side, which is great because it's also in the reactant side in the target equation, so that's fine. Now, I'm hoping you can see we have 1 mole of chlorine gas atoms here on the product side of this equation. You have this also on the reactant side, although it's 2 times 1/2, which is 1 mole. So you can cancel out here the chlorine atoms. So that is gone. Okay, the last thing we need to get rid of are electron terms. And so here we have an electron term on the right side, and that cancels out with the electron term in the sodium equation on the left side. So we get rid of these. And so what you can see now is we are left with the target equation. So here's the chloride ion, which is one of the reactants. And here's the sodium ion, which is one of the reactants, and we're left with sodium chloride solid, which is a product. So what you can do is you can add up these numbers here, And you should get that answer that I have on the screen, which is negative 788 kilojoules per mole. Okay, so let me go ahead and erase this and we'll move on to the next problem. Okay, so I want to go on to the next problem. So here it is. And so if I can blow up the slide, it says determine the heat of formation of the ionic compound aluminum fluoride from its elements aluminum and fluorine using the enthalpy changes of the reactions below. Okay, if I can reduce the slide. So this one is a little tricky. And maybe the most difficult part is trying to figure out what the target equation is. And so now, importantly, the target equation is not a lattice energy for aluminum fluoride. In other words, we're not going to write an equation that describes how aluminum ions get together with fluoride ions to form aluminum fluoride. Instead, the target equation is a heat of formation equation for aluminum fluoride. So there, the product is aluminum fluoride, but again, the reactants here are going to be its constituent elements at room temperature and pressure. So let me go ahead and correctly write this equation. This is a little tricky. All right, and so here what we're trying to do is we want an equation that describes the formation of the ionic salt aluminum fluoride, which has this formula AlF3, in the solid state. But again, we're not bringing together individual ions. What we're bringing together is the elements that are part of the compound in their natural states at room temperature and pressure. So aluminum is a solid at room temperature and pressure, and then fluorine is a gas at room temperature and pressure. Okay, so far so good. Now, you can see there's some problems here. And so one problem is that this equation is not balanced. So one of the things you may already know is that with heat of formations equations for compounds, we can only have 1 mole of the compound. So we can only have a 1 here, and so we can't really adjust the coefficients here. So how do we balance the fluorines? Well, the fraction you want is 3 halves. So let me explain why that's the case. Let's think about how many total atoms here are represented on the left side of the equation here for fluorine. It's going to be 3 times 2, which is 6, divided by 2, which is 3. So really, when you see this, it's really 3 fluorine atoms, which balances the 3 fluorine atoms there. So that is the target equation. So what we're going to have to do is take all those given equations and adjust them as necessary, and then cancel out symbols such that we're left with the target equation. So I'm going to go ahead and write out all these equations on the board. Okay, so what I've done is I've written out all the equations that you see on the screen on the board, and so let me just quickly go through what these are. So this first equation here is the energy involved with subliming solid aluminum metal into gaseous aluminum metal. In other words, you're taking solid aluminum atoms and just separating them out to become gaseous aluminum atoms. So this is a sublimation. And then you can see it's an endothermic reaction. Its change of enthalpy is 330 kilojoules per mole. So this next reaction is where you take gaseous aluminum atoms and you ionize them by pulling off 1 electron. So this is the first ionization energy. So this is IE1, and you can see how much energy is required for that. But then we're given another equation. We're taking now the aluminum ion and hitting it with more energy, and we're getting another electron knocked off. So that leaves you with aluminum 2+ ion. So this is the second ionization energy here. And then the last ionization energy equation we have is where we have aluminum 2+, and we're hitting that with even more energy, and you're getting aluminum 3+, and electron is removed. And so this is the third ionization energy. Here, you're taking diatomic fluorine molecules, and you're just breaking the bond between the 2 atoms in the molecule and separating out the fluorine atoms. And so this is a bond energy. And then here, what we have is we have neutral fluorine atoms in the gaseous state, and we're adding electrons to them to form gaseous fluoride ions. And so this here is an electron affinity. And then this final reaction is you're taking aluminum ions and you're adding them to fluoride ions to give you the solid aluminum fluoride. And so this is an equation that describes the lattice energy of the formation of solid aluminum fluoride from its constituent ions. And you can see this is a very exothermic reaction. Okay, so the goal is we have to modify these equations, whether it be by flipping them or maybe adding coefficients, such that everything cancels out except the symbols that are found in the target equation. So let's examine what is found in the target equation. So one thing I immediately see that the target equation has as a product is solid aluminum fluoride. There's only one equation here that shows that, and that's the last equation here, which I think is the, what, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, seventh equation down. And so you can see in the seventh equation down, the aluminum fluoride solid is also as a product. And so the good news is we don't have to flip this over. Furthermore, in the target, we have 1 mole of this and we have 1 mole of this. And so we don't have to add coefficients either. So that's really good news. Okay. So another thing that I see, which is good news, is that here in the target equation, we have aluminum in the solid state as a reactant. And I only see that once up here in these equations. It's in the first equation. And look, it's aluminum in the solid state as a reactant. So that means with this first equation, we don't want to flip it, nor we want to add any kind of coefficients to it. So that's good news. So let's go ahead and see if we can sort of deal with the aluminum before we deal with the fluorine. So like I was telling you before, we want to keep aluminum here in the solid state, but you want to get rid of everything else here that's aluminum. But the good news is everything's going to cancel out by itself. Let me show you how that works. You see, you have aluminum in the gaseous state here in this first equation. That is a product, but in the second equation, it's a reactant. So that goes away like that. So that's nice. Okay, and then we want to get rid of this Al plus ion here in the gaseous state. It's going to be here in the product side, but in this equation, it's on the reactant side. So we get rid of that. So that's good news. All right, okay. And then here we have aluminum 2 plus. In this equation as a product, we have it as a reactant. That goes away. Excellent. So good news all around. Okay. Now we have aluminum 3 plus here as a product, but the nice thing is here in this equation, it is a reactant. So we can get rid of this. Yeah. So that's good news. So basically, we have gotten rid of all the aluminum symbols except the one we want to keep, which is aluminum solid. That should be in the reactant, and we want to keep that because it's in the target equation. Okay, so now let's deal with fluorine. Okay, this is going to be a little trickier. And so what I want you to notice here is in the target equation, we don't have fluorine ions. We don't have fluorine atoms. We have diatomic fluorine molecules. And so what's worse is that we have a coefficient here of 3/2. And so what we have to do is get rid of all of the symbols for fluorine except the fluorine molecules. And we have to have it such that it's 3/2. Okay, so what do? Okay, so there's one thing that I can see which may help, which is kind of interesting here. So remember, in the target equation, we want diatomic fluorine molecules. You can see here in this equation, 1, 2, 3, 4, 5, 6 one down, as a product, we have fluoride ions. So we got to get rid of that. But here in the seventh equation, we have fluoride ions, but we have 3 of them. So this is kind of interesting here. So what I'm going to do is I'm going to multiply this whole equation by 3 here. Okay, and so I have to remind myself, I'm going to take this equation, which I didn't flip, and multiply it by 3. Why do I want to do that? Well, the reason is this. Here we have 3. Well, let me go ahead and rewrite this. That might be a little bit easier to see. So I'm just going to rewrite this like this. Yeah, I want to rewrite it. All right, so we have 3, 3, and 3 like that. Okay, so now you can see some neat things. And so you can see here we have 3 fluoride ions on the product side. We'll cancel out with 3 fluoride ions on the reactant side in this equation, so that goes. Yay. Okay. But there's something else that's kind of interesting that happens. You see you have 3 electrons here on the reactant side. Here we have 3 electrons on the product side, so those cancel out. So the electrons go away. Yeah, so that's good. Okay, now's where things get kind of interesting. Okay, so here we have 3 moles of fluorine atoms. But again, we want diatomic molecules of fluorine. So what do we do about that? Well, you can see what we want to do is go back to this other equation here. It's, I guess, the 5th one down. It's diatomic fluorine molecules gives you 2 fluorine atoms. And so what our goal is to modify this equation such that we will have 3 halves of diatomic fluorine molecules, and we'll have 3 fluorine atoms that can cancel out with 3 fluorine atoms here. So let me go ahead and just say maybe what we want to do here is put 3 halves here, like that. And so just to give me some room, I'm going to erase, well, so we get 3 halves F2 gas gives you 3 times 2, which is 6, divided by 2, which is 3. So it's 3 fluorine atoms in the gaseous state. So that works. So what we essentially did was this. We took this equation and we found when we multiply it by 3 halves, then we get 3 halves diatomic molecules and we get 3 fluorine atoms that we get rid of. So for the bond energy equation, this one here, we're going to take this, we didn't flip it, and multiply it by 3 halves, like that. Okay, so this is where I did my work. Let me just get rid of this. And so what you can see now is that here the fluorine atoms will cancel out, and you're left with 3 halves F2. So let's just confirm again, we have all that we need. We have 1 mole of solid aluminum. We have 3 halves of diatomic fluorine molecules, which is what we want. And then here, in the last equation, we got aluminum fluoride solid. So this is going to work. Okay, so what I'm going to do is the final math here. So I'm going to first deal with the 157 times 3 halves. And what I got earlier was 235.5. Okay, now what we have here is negative 328 times 3. And what I got earlier here was negative 984. So let me just go ahead and get rid of this now. Okay. Let me just move these here. 235.5 plus negative 984. So if you take all these numbers that I have here, plus 330, plus 578, plus 1817, plus 2745, plus 235.5, minus 984, minus 6231, you should get the enthalpy change of the formation here of this equation, which is negative 1510 kilojoules per mole. Okay, thank you for listening. We'll see you next time.